12.4 Reactions of alcohols, thiols, aldehydes, and ketones. You'll notice here's a flaming dessert is prepared using heat from the combustion of an alcohol. A typical combustion reaction, we have our carbon, and when we have heat and oxygen, you'll notice our products are CO2 and water plus energy, like what we've learned back in some previous chapters about combustion reactions. Here's an application with our ethanol. Now, the learning goal in this section is to predict the products of dehydration and oxidation of alcohols, predict the products for the reduction and oxidation of aldehydes and ketones. Now, alcohols undergo dehydration when heated with an acid catalyst. The loss of hydrogen and OH from adjacent carbon atoms, producing an alkene and water. So if you'll notice here, the reason why it's called dehydration, think about, when you're dehydrated, you have lost some of your water and you need to get more water in you because you're dehydrated. Well, they're using that word and actually applying it to this process of losing an H and an OH, which we all know is water. So you'll notice that with this alcohol, we can, with heat and an acid catalyst, we're going to dehydrate it, making an alkene. With oxidation and reduction, the biochemistry of our body incorporates the oxidation and reduction processes in the metabolic pathways and the ATP production. If you've taken some biology classes or microbiology, you probably have heard of those words, or the Krebs cycle, or the citric acid cycle. Well, that all uses oxidation and reduction concepts of aldehydes or ketones or alcohols that we're going to learn in this section. We're going to apply the concepts from this section 12.4 to how the body uses energy in chapter 18, which, by the way, encompasses all of chapter 18. In organic chemistry, oxidation reactions increase the number of carbon to oxygen bonds by either the addition of oxygen or the loss of hydrogen atoms. Whereas reduction is just the opposite. They reduce the number of bonds between carbon and oxygen atoms by addition of hydrogens or loss of oxygen. Now then, oxidation of primary alcohols. Alcohols undergo oxidation, which increases the number of carbon and oxygen bonds. So you'll look at this. So primary alcohol, so here's a primary alcohol. Remember back in another section you learned a primary alcohol was if an alcohol is attached to a carbon that's only attached to one other type of carbon chain. So they are oxidized to produce an aldehyde. Well, the only problem is unless you do something special to stop it, aldehydes are also then further oxidized to carboxylic acids. So for this level of chemistry, we'll just say that, let me go back to this slide, that when primary alcohols are oxidized, yes, they go to an aldehyde, but they end up with a carboxylic acid. Now you might go, what's a carboxylic acid? Carboxylic acid has this functional group of our carbonyl group with an OH. So the OH is not an alcohol, so don't think, oh, that's an alcohol. No, when the OH is attached to a carbon of a carbonyl group, that functional group is called a carboxylic acid, and they have their own special properties. Now let's see what a secondary alcohol goes to. So when we have the oxidation of a secondary alcohol, when we have our oxidation, you will notice we increase the number of bonds to our carbon to oxygen, but you'll also notice the end result also decreased and took away 2 hydrogens there. So a secondary alcohol is oxidized to a ketone. And this is actually why you had in another section to learn why to be able to identify primary, secondary, tertiary alcohols, because depending on the kind of alcohol, they're going to react to produce different types of other organic compounds. Now, tertiary alcohols do not readily oxidize because there's no hydrogen atom on the carbon bonded to the OH, So that is not going to produce a reaction like this. So for this class, we're just going to say if you have a tertiary alcohol, the reaction does not go, and so there is no product. So here's just an example. Here we have methanol. And sometimes when you see and hear about people in other lands that have died because they have drank some bad alcohol, it's because the people that made the bad alcohol didn't do it correctly, and there was some methanol in the ethanol substance, and methanol is highly toxic. Now you'll notice it's found in windshield washer fluid, sterno paint strippers, and what it is it is readily absorbed by the human body, whether you're drinking it or whether actually it's you just have it on your skin. It's oxidized to, first of all, this methanol, this aldehyde, which is formaldehyde. So it's oxidized to formaldehyde, which we know formaldehyde is not good for our body, and then it continues to the carboxylic acid, the methanoic acid, which is formic acid. And so again, we have a primary alcohol, which ends up being oxidized by our body to methanoic acid. Now, you can test for aldehydes or ketones through the use of the Tollens test. So this is a very famous test. It's also called the silver mirror test, and it's pretty amazing. I know that when I was teaching organic chemistry, the year-long class, we would get different glassware. Students would bring it in, and we would create the reactions to silver, our particular glass tubings, and glass whatever it was, and it was kind of neat. It was really beautiful, actually. It was one of the students' favorite labs. But anyway, in the Tollens silver mirror test, it is used to distinguish between aldehydes and ketones. So the Tollens has this silver ion, which it does easily oxidize aldehydes, but it does not oxidize ketones. So ketones are not oxidized under normal conditions. That's kind of a key point here. And so you can test by, it's so obvious, is that when you throw in the Tollens mixture into your item, if you have aldehydes, you're going to see silver coat out. I mean, that's pretty obvious. And so it's a positive test for aldehydes. But if it's just ketones in your unknown solution, then you will not get any silver to coat out. So you'll know, oh, there's no aldehydes in here. So the Tollens test is used to distinguish between aldehydes and ketones. Aldehydes react, ketones do not. Now thiols, if you remember thiols, where the sulfur is in the compound, and if you remember right, sulfur is right under oxygen in the periodic table. So there are some similarities of reactions. Now, as I just briefly mentioned about the thiols undergoing oxidation, the product is a disulfide. So they're going to lose these two hydrogens here from two different protein chains in the process of oxidation. Remember, oxidation, one of the things could be a loss of two hydrogens. And so what it does, it connects them. An example of the use of this, or your body's use of this, is your protein in hair is cross-linked by the disulfide bonds found in our amino acid cysteine. So we'll talk a little bit more about that in Chapter 18. All right, the opposite of oxidation is reduction. Reduction of aldehydes and ketones. In the reduction of organic compounds, aldehydes and ketones can be reduced by using sodium borohydride or hydrogen as the catalyst. The number of carbon to oxygen bonds is reduced by either adding hydrogen or losing oxygen. So remember, it's the opposite. Reduction is the opposite of oxidation. And so you use a catalyst for the addition of hydrogen. So a nickel, platinum or palladium catalyst is needed to do it. So that's why sometimes over the arrow you will see our platinum or our nickel. So when we add hydrogens, the hydrogens will end up adding to the double bond, one to the carbon here, one to the oxygen. So you will notice that this carbonyl group here is reduced. Okay? And so the carbonyl group of this aldehyde is reduced to an alcohol, and it's a primary alcohol. Whereas a ketone, when it gets reduced, remember addition of this hydrogen here and a hydrogen there, a hydrogen across the double bond of the carbonyl group, then we get ourselves an alcohol. And what kind of an alcohol? A secondary alcohol. The applications of dehydration, oxidation, and reduction reactions of organic compounds discussed in this section may seem foreign and unrelated to anything you think you need to know. However, that's not the case. In this section, we learn the actual chemistry of these processes. We didn't say, oh, this is how it's applied, now apply this. We're just learning the steps here. That is the first necessary step in order to better understand what's happening in how our body's metabolic process works. Chapter 18 applies these reactions to the biological processes. And so by learning the chemistry here, we can understand the biological processes in Chapter 18. I once had a student say that learning this and learning Chapter 18 in chemistry, in this chemistry class, actually helped them finally understand microbiology. And so that was that's such a compliment to the chemistry. But so topics in which we're going to use these reactions from this section are digestion, glycolysis, citric acid cycle, also known as the Krebs cycle or the TCA. So you can see that you have many things in which we're going to use these concepts. So let's do our learning check. Let's see if we can get the right product for the oxidation. So we first have to identify, is this what is this? Okay, this is an alcohol. It's not a primary alcohol, it's a secondary alcohol. So we know that secondary alcohols, when they are oxidized, form ketones. So we go through here and we look for a ketone, and B is our only answer. Now then, learning check here. Select the product when we have this alcohol that undergoes each of the following reactions. So we have a primary alcohol that is going to go through two different oxidation reactions. So we know that primary alcohols are first oxidized to an aldehyde, but it doesn't stop there. So B right here is this aldehyde, but the reaction continues to form a carboxylic acid. All right, so let's see if you know, we don't need to name it, but let's see if you can write the structure when each is mixed with Toland's reagent. Now remember, Toland's reagent is that silver ion, and so it's the test between aldehydes and ketones. So only aldehydes test positive using the Toland's reagent. So butanol, well, that's an aldehyde, so it's going to be a positive reaction. Ethanol, that's an aldehyde, so there's going to be a positive reaction. Butanone, that's a ketone, so you're going to get no reaction with the Toland's reagent. So let's look and see. So we notice here's our aldehyde, and we get our carboxylic acid with our Toland's reagent. So here's our aldehyde, our ethanol, also known as acetaldehyde. With our Toland's reagent, it's going to react, and it makes a carboxylic acid. So here's our ketone. We know that there is no reaction with a Toland's reagent. Why? Because ketones are not easily oxidized.